in this video, we're going to continue considering this idea of frontogenesis, but now we're going to consider it in both horizontal directions together in a simplified version. And so in our 2D frontogenesis equation, we are going to consider the effects of deformation and divergence together to see if we can come up with a reasonable way to get frontogenesis in a reasonable amount of time. And so first, let's go ahead and write our 2D frontogenesis equation. So we are simply taking some of the previous equations we learned about and reducing them down to what is better known as the Pedersen frontogenesis equation, where F equals 1/2 the magnitude of the gradient on a pressure surface of our potential temperature multiplied by the resultant deformation d times the cosine of 2 times the angle between our axis of dilatation and our isotherms, minus delta, which is our horizontal divergence. And so here I'll just note again, d is the resultant deformation. Delta is our horizontal divergence. And B here is the angle between our isotherms and our rotated axis, the axis of dilatation. And so what we're really seeing here are the effects of both deformation and confluence/difluence on our ability to create a front. And so in order to inspect this, we're going to want to look at a graphic. But before that, we can state that F is going to be greater than 0, and we will have frontogenetic processes if our axis of dilatation which our axis of dilatation is the deformation 2 line, where deformation 2 is our dv dx plus du dy term. That's du dy. There we go. And that it lies within 45 degrees of the isotherms. So what does this mean? Let's go ahead and take a look at a graphic from the Bluestein textbook. We're going to scroll down for this graphic here. Here is an example of a 2D field where we have our potential temperatures signified here with our dashed lines and our resultant field in our solid lines. And so we can then assess here our axis of dilatation as this kind of line right here, one going out this way, one going out this way. That's our axis of dilatation. Versus then our axis of contraction is where we have our air coming together, contracting, if you will. And here we see B, that angle between our axis of dilatation and our isotherms. And so we can see here that this angle is less than 45 degrees. And so what we should notice is that our isentropes to the south are going to be pushed up this way. Our isentropes for the north are going to be pushed down to the south, such that we're going to concentrate our isotherms here, such that our frontogenesis is going to be greater than 0. Similarly here, we see our angle B is greater than 45 degrees. When it is greater than 45 degrees, our axis of dilatation is helping to spread our isotherms out such that we have frontogenesis less than 0. And so we can combine these to see this effect. And this is but a simple way to illustrate both kinematic functions of deformation and divergence acting here to increase or decrease the strength of the magnitude of our gradient in potential temperature. But does this make a front in a reasonable amount of time? And so let's scroll back up here and think a little bit about what we can say about how much time this might take to work. And so let's consider just our confluence. So considering confluence only, we know that that term is our d theta dy dv dy term in one dimension. And so we can assume that our convergence term here is but a constant. So minus dv dy equals a constant, which that constant might be something on the order of 10 meters per second per 1,000 kilometers. And so if we make this assumption, we can then create a differential equation to help us solve this case, such that we can say our new gradient in y is equal to our original gradient in y, d theta dy naught, times e to the k sub t. Here, this k is our convergence term, our confluence term. And so that we can estimate then the time it's going to take to double our temperature gradient, or about double our temperature gradient here. We can assess at what time we are going to e-fold. Okay, and so we're essentially talking about the e-folding time due to confluence. And so the way we can do that is we're trying to solve for the time in our equation up here, knowing that we can substitute in k for our 10 meters per second per 1,000 kilometers. And so the way we do that is if we put in ratio our new temperature gradient minus d theta dy over our initial temperature gradient d theta dy naught, this will equal e to the k sub t. To get rid of the natural log, and we know that this wants to go up by a factor of e, we can say that this ratio we want to be e. So now we have e equals e to the k sub t. If we take the natural log of both sides, we can get ourselves into kt equaling 1, or t equaling 1 over k, which is going to be approximately 1 day when we figure out all that's said and done. So that it would take 1 day's worth of confluence and convergence to generate about a doubling or an increase in the factor of 2.71, the value of e, to increase. And from observations, we know that this is just too long. Kinematics cannot in and of itself explain the strengthening of our temperature gradients, because our temperature gradients can double on the order of hours, not on the order of days. And so we have to look to other aspects to determine how can we actually get a front in a reasonable amount of time. Kinematics will not be enough. And so in our graphic here below, even with 2D frontogenesis, this would still fall under kinematics and not be enough to generate our front in a reasonable amount of time. So what about QG frontogenesis? QG frontogenesis, instead of taking into account only kinematic variables, here we can take into account quasi-geostrophic processes as well. This is a cross-section of potential temperature from a model using QG frontogenesis as its dynamics. In this scenario, what we find is that this simple modeling is still, 1, too slow. 2, our frontal zone does not slope properly. Recall that, remember, any front should, if we draw the ground and draw some isentropes, should bend only towards cold air. Here we do have some bending towards cold air, but we also have some bending towards warm air. And if we were to look at this area just out ahead of our discontinuity, we would see as we go up from the surface, potential temperature decreases a little bit. And we know that where potential temperature decreases with increasing height, that is an absolutely unstable environment. And so then we also have regions of static instability here. So not only do our isentropes not all slope towards the cold air, but we have regions of static instability instead of regions of just high static stability, which we know to be associated with fronts. Finally, we can also have regions of both cyclonic and anticyclonic vorticity with a front, which we should only get cyclonic. So our kinematics are too slow and don't allow us to get fronts in a reasonable amount of time. QG dynamics, again, don't allow us enough. It's still too slow. We have regions of cyclonic and anticyclonic vorticity which don't occur in reality, and regions of static instability which don't occur in reality. So from all of these, we're going to need a new set of equations to help us actually get to a realistic frontogenesis perspective. And for that, we're going to need to add more pieces back in to our QG equations to develop the next set of equations that we can use to then get frontogenesis in a realistic amount of time.